This is an overview for linear regression. On the plot, you can see data points. Every xi has a data point y data I, and their total of n number of data points. There's a line passing through that. That's the linear regression model for this data set. So for every xi, there's a y model I. The departure, the vertical departure on that graph between the data and the model is called the error, or the residual. And so that's y data I minus y model I. In linear regression, we're seeking a line that best fits the data. And what that means is our y model is a0 plus a1x, where a0 is the offset and a1 is the slope. The line that best fits the data minimizes the sum of the squared error. So it's the smallest SSE that can be found. An important variable is the residual degrees of freedom. This is symbolized with a nu here, that curly v, and it equals the total number of data points n minus 1 minus the polynomial order. For linear regression, the polynomial order is 1. The mean squared error is a quantity that's often talked about. It's the sum of the squared errors, or SSE, divided by the residual degrees of freedom, nu. So it's important to say that the mean square error is not simply SSE divided by n, rather it's SSE divided by nu. Something we see a lot of is the root mean square error. And here we're tacking on another process. We're taking the mean square error and then taking the square root of that. And very often the root mean square error is reported to characterize how well the model works, how well it fits the data. The next quantity is the mean. We're all familiar with this. I write it as y data with an overbar equals 1 over n, that's the number of data points, and then the summation of each data point, y data I. The mean is involved in something much less familiar to us, the total sum of squares, or TSS. So for the total sum of squares, first we take the difference between each data point and the mean, square it, and then sum it up, as is shown here. Now we get to the squared correlation coefficient. This is something that is familiar to many of us. That's r squared. It can be defined in many ways, but here I'll give you one formula, which is 1 minus the sum of the square error, SSE, divided by the total sum of squares, TSS. So we've got 1 minus SSE divided by TSS. That equals r squared. And r squared ranges from 0, where the model doesn't fit the data at all, to 1, which is a perfect fit. For any regression, it's actually more appropriate to talk about the adjusted r squared. So here, r squared ADJ is the adjusted r squared. It equals 1 minus the quantity, 1 minus r squared, which is above, times the quantity n minus 1 divided by nu, where n is the number of data points and nu is the residual degrees of freedom. What the adjusted r squared accounts for is the reduction in the degrees of freedom associated with fitting model coefficient. It's more appropriate than r squared for characterizing how well a regression model fits the data. That said, r squared, non-adjusted, is what's often reported. That's not going to cause a problem unless you're comparing models of different orders, say a linear fit to a quadratic fit. The quadratic fit might look better and have a higher r squared, but the r squared adjusted might actually be lower because the degrees of freedom have been reduced. So it's best practice actually to report both and then use the adjusted r squared.